Hello everyone. In this section, we are going to study the stability of equilibrium points. Equilibrium points, total force acting on the object is gonna be 0. So this means total force is F is gonna be 0. This is the equilibrium point. We have two types of the equilibrium point. It's a stable equilibrium point or unstable equilibrium point. For example, potential energy curve is expressed this way. If the particle is placed at the bottom of a ball, so in this situation, this point is the equilibrium point. Because the force is proportional round u round x, the derivative is 0 at the bottom of this curve. So this is the equilibrium point. Also, if you find that this curve force is 0 at the top of this curve, so also this point is the equilibrium point. Then we are interested in which one is a stable equilibrium point and which one is an unstable equilibrium point. We need to consider the displacement of the position of the particle. So in this case, the position is moved to right or left. Then what's happened, we are going to discuss. When the particle is moving to the right, this is new position. This particle starts going to down once you release the ball. And we could observe the oscillational motion around the equilibrium point. Because of the particle don't move away from the equilibrium point, we call that this is stable equilibrium point. But in the case of the right figures, if we move the object a little bit in the right, then these particles, actually the force is acting on this particle, this direction. And this particle is moving away from equilibrium point. So we call in this situation, the equilibrium point is unstable. So we need to determine the stability of equilibrium point. So we discovered 5 equilibrium points, L sub 1, L sub 2, L sub 3, L sub 4, L sub 5. So we are interested in finding the stability of these 5 Lagrange points, equilibrium point. Consider the Lagrange point L sub 1, L sub 2, L sub 3. The potential curve is obtained by the sum of the two potentials, centrifugal potential drawn by the yellow curves, and the gravitational potential drawn with the blue curves. Then total potential is drawn with the red curves. Then we could easily find out equilibrium point, Lagrange point. If you remember the previous curves, so these curves correspond to the right figures, these figures. All the 3 curves is the equilibrium point is placed on the top of the potential curves. Then if the particle in a little bit different position, this particle is moving. Moving away from the equilibrium point. So we could easily imagine that these equilibrium point might be unstable. Then to find out the stability of the equilibrium point, we usually use the linear stability analysis. Linear stability analysis. So we transform the equation to the linearized equation. This linear stability analysis is a very useful technique to examine the stability of an equilibrium point. because the nonlinear equation is quite difficult to solve. So if you look at the equation for the u, so x squared and the v squares, and the r sub 1 and the r sub 2 is this complicated function. So this is not proportional to the x or y's. So these terms we call nonlinear terms. Round u, round x, round u, round y, round u, round z should be expressed with the linear terms. So if we consider x squared terms, derivative of the x squared becomes 2x. Then round u, round x becomes the linear terms. So these terms appears as a linear terms. Also y square is the same, but in the case of the r sub 1, r sub 2, even if you find the derivative of the r sub 1 and r sub 2, it becomes a nonlinear terms. So we'd like to linearize these terms, gravitational terms. Then at the Lagrange point, so k is changing 1, 2, 3, 4, 5. We have 5 Lagrange points. So equation is expressed with these 3 equations. At the Lagrange point, acceleration and the velocity is 0. So this means derivative with respect to x, y, z is going to be 0. This is a condition for the Lagrange point. Then we'd like to consider the displacement from the Lagrange point. So if you consider Lagrange point is some x sub k, this is Lagrange point, this is the x coordinate. So Lagrange point, sometimes it's going to be the bottom of the ball. So in this situation we are going to consider. Then particle is here. Then at the Lagrange point, slope becomes 0. So this slope is 0. Then we'd like to consider small change of the position of the particles. So this is x. So this difference, x minus xk, is we use a capital X. This is x minus x sub k. This is a capital X. So we expect x, capital X, is much smaller than the x sub k. This means a small displacement. So we'd like to consider small displacement from the Lagrange point. So x, y, z is expressed difference from the Lagrange point. At the Lagrange point, gk, this is gk, g sub k is a 0, always 0. So in the case of the lower case of the z, exactly same with the capital Z. So if we consider derivative of the x, y, z with respect to times in the next line, Lagrange point, derivative becomes 0. So it becomes x dot equals capital X dot. Lower case of the y dot is equal to capital Y dot. Also second derivative is going to be 0. Okay, lower case of the x, y is going to be 0 at the Lagrange point. So this is going to be 0. So lower case of the x2 dot is equal to the capital X2 dot. Lower case of the y2 dot equal to capital Y dot. Because the acceleration and velocity at the Lagrange point is equal to the 0. Then we'd like to express the potential near the Lagrange point. This is a Taylor series expansions of the potentials up to the second orders. So approximate potential as a parabolas. This leading the linear force. So if you consider the second orders, as I explained, it becomes first order force. So it's leads to the linear force. We ignore potentials. This because we consider small displacement. So at Lagrange point, as I explained, the derivative becomes 0 at the Lagrange point. Also, solution should be symmetric about the xy planes because the Lagrange point exists on the xy plane. So this means g equals 0. If you just calculate second derivative, it becomes minus 3 gm sub 1 over r sub 1 5 x plus mu r sub 1 2 g minus 3 gm sub 2 over r sub 2 fifths x minus 1 minus mu r sub 1 2 g. So if you substitute g equals 0, z equals 0, this term is going to be 0. So we proved this one. And also we could calculate the second derivatives of round y, round z. So also this case is minus 3 gm sub 1 over r sub 1 5 gy minus 3 gm sub 2 over r sub 2 fifths gy. So again g is 0. So this becomes 0. Okay, so we proved these formulas. Then we substitute. Then potential is just we keep the several terms. So first derivative term is going to be gone. So second derivative we have. And the second derivative, partial derivative round x, round y. Then you could calculate the partial derivative of u with respect to x, y, z. Then u sub k, so this quantity is a constant quantity. These are constant values because we have to substitute the coordinate of the Lagrange point. So these are constant values. Then partial derivative with respect to x, just only we have two terms. And then partial derivative with respect to y, also we have two terms. And the partial derivative with respect to z is just we have single terms. Then we substitute these three equations into the original differential equations. Then equation becomes linearized. In the equation we have three equations. X 2 dot minus 2 omega y dot. And this is first linearized equation. Linearized force we have. And also equation for the capital Y. We have linearized equations. And also G, we have a linearized force. We have equation becomes a linearized. So this equation can describe the motion of the particle when the displacement is a small case. Okay, this is the end of this session.